oxygen nucleophiles. That was what we ended with last class, was oxygen nucleophiles. And today we're going to start section 19.6, which deals with a nitrogen nucleophile. So if you have a carbonyl of an aldehyde or a ketone, you can imagine that a nitrogen could attack the electrophilic carbon and the carbonyl. Well, how is that going to happen? Well, it says here that under acidic conditions, an aldehyde or a ketone can react with a primary amine to form a new functional group to us. It's called an imine, And sometimes we refer to an imine as a Schiff base. It's named after somebody named Schiff, you can imagine. So sometimes we call an imine a Schiff base. So you see what's happening here. We're taking benzaldehyde and then we're treating it with a catalytic amount of acid. Here they're using methylamine, which is a primary amine. Remember, we need a primary amine. That's a primary amine. And this little subtract H2O, what that refers to is the loss of water, right? We're losing water, and you can clearly see that we're losing what? We're losing the oxygen. Oops, we're losing this oxygen, and we're losing these two protons here. So we've lost H2O in the reaction. Now, instead of a carbonyl, instead of a carbon with a double bond to oxygen, we have a carbon with a double bond to nitrogen. And since nitrogen always has to have 3 bonds and 1 lone pair, the other bond is to the methyl group. Now, something I want to point out here before we move along is that you can also do this same reaction to make an imine, and you could do it with ammonia instead of a primary amine. So let me just draw. If you had the same old benzaldehyde, okay, and you took it and you treated it with a catalytic amount of acid, that's what the square brackets mean, and some ammonia, and of course you lose water. What you would end up with in that case is you end up with the carbon with a double bond to the nitrogen, same as before, but now instead of a methyl group, you'd have another hydrogen out here, okay? So again, we can do it with a primary amine, or I'm going to write here, or ammonia, and we end up with a Schiff base or an imine. So again, an imine is called a Schiff base. Now, you might be wondering about the mechanism of this reaction, and I'm going to show it to you on the next slide. It looks a little bit daunting when you first glance at it, but we want to think about it in a couple of, sort of break it up into 2 parts is what we'll do. So let's take a look at it. And the first step is actually a nucleophilic attack. Now, thinking about the first step of acetal formation, when we looked at an oxygen nucleophile, the first step was always a proton transfer, right, to protonate the carbonyl. However, if we were to try to protonate the carbonyl first to render it more reactive, to render it more electrophilic, and what I mean is to try to protonate it to make this so that it's a super powerful electrophile. The problem with that is that in order for us to do that, in order for us to make this, what would happen is we would protonate all of the amine. You'd have none of the amine left over, so there would be no amine to do the nucleophilic attack. And so I'm going to address the whole idea of what the acid will be. But the acid that's going to do the proton transfer in the next step is actually probably going to be a protonated ammonium ion. So here you see they have the primary amine. So what's doing the proton transfer would actually be the R group with the nitrogen, but having 3 hydrogens. So it's actually an ammonium ion, which obviously isn't as acidic as something like hydrochloric acid. Okay, so now that we've got that out of the way, we do the nucleophilic attack, the proton transfer, then we do another proton transfer, and we end up with this interesting intermediate here that you call a carbonyl amine. It's a new functional group. You need to know it. And the carbonyl amine is kind of funny. I mean, the way I think about it is I always think, okay, well, it's a carbon with a hydroxyl, so it's like an alcohol, and it's like an amine, both on the same carbon. So that's a carbonyl amine. And remember, we end up losing water in this reaction, but we haven't lost any of the atoms that would make up the water molecule yet, because we need to lose this hydrogen, and obviously an oxygen. So what's going to happen next is that some of that acid is going to protonate the hydroxyl to convert it into a good leaving group. You lose water, and the last step is also another very key step. It's another proton transfer, but notice that the proton is transferred from the nitrogen to form the imine, and we're going to see that when we form a different functional group called an enamine that this last step is slightly different. So we'll get to that in a second. Again, what I was talking to you about, if you didn't quite follow me on what I said about the pH or the acidity of the reaction, remember that when we used acidic conditions, again, for when we had an oxygen nucleophile, we used a strong acid to protonate the carbonyl, make it a super reactive electrophile. The problem with that here is that if you were to treat it with a strong acid and you have an amine in the reaction, all you're going to end up with are ammonium ions, right? So you're not going to have any of the amine left over to do the nucleophilic attack. So that's not going to work, all right? It's not going to work at all. And so in order for the amine to be formed, in order for this reaction to work, the reaction that we're talking about, the first reaction of the day, to get it to work, the pH, excuse me, has to be right around 5. I think the book says 4.5. I mean, it's neither here nor there, but you can see that, you know, we have the maximum reactivity or the maximum reaction rate here, right around pH 4.5. And if you increase it too much, right, then it's going to be too basic. And what the problem when it's too basic, I'll show you, is that it's not basic. If it's not basic enough, the reaction won't work. And of course, if it's too acidic, then everything gets protonated. So anyhow, there we go. That's really all you need to know. So what did I put here? I just want to read my slides. Lower pH, everything's protonated. Yep, that makes sense. Higher pH, there's not enough acid to even catalyze the reaction. In that case, the words I was looking for here is if the pH is too high, I mean, in that case, it's not even acidic enough to do this. You won't even protonate that. So, I mean, it's useless then. Anyhow, I've only made a few amines in my life, but I know enough to tell you that you do kind of have to fiddle with it and fuss with it in order to get that pH just right. So there we go. Amine formation, a new functional group. All right, you could practice drawing the amine on your own time. You know, you've got a carbon, it's got a double bond to a nitrogen, right? And then you've got an R group here. So these could all be different R groups. And this one could be a hydrogen, okay? But this is an amine, which again is a shift base. And amines are going to come up again later on in this lecture. Well, I want to move on and talk about what if we were to try something similar, okay? The same kind of acidic conditions. And when I say acidic, I mean slightly acidic, you know, that pH of around 4.5, you know, in that 4 or 5 neighborhood. What happens if you use a secondary amine? Okay, what happens if you use a secondary amine? This is a secondary amine right here. What you end up with then is you get a different functional group, and it's called an enamine. The enamine has no sassy name like a shift base or anything like that. An enamine is just what it is. It's just a good old enamine. But the enamine, you have a nitrogen. It's got 3 R groups, but on the carbon, one of the carbons is going to have a double bond. So that's how I remember an enamine like that. I also took a class where we did like a whole chapter on enamines when I was an undergraduate. So I kind of remember the enamine pretty well. But again, it requires acidic conditions in order to get this reaction to work. And we have to have them tuned just right. Now, if you understood the mechanism of the formation of an amine that I just went over in quite a bit of detail with you, well, the good news is that all the first steps, everything, all of this, really all of this, I should say, all of this is the same as the formation of an amine. So if you understood nucleophilic attack, 2 proton transfers, you form the carbonyl amine. Now, instead of a hydrogen here, you have a second R group. Then you do a proton transfer, you lose water. But it's the last step that is different than the formation of an amine. Because again, when we formed an amine, you remember the nitrogen had at least 1 hydrogen on it. Well, here it has no hydrogens. And so in order to deprotonate, to eliminate this positive charge, it has to go to the carbon that is next to the carbon of the double bond and take one of the protons off of there. And then we form our enamine. So to summarize, you know, again, the reaction mechanisms are very similar, right? When we form an amine, we can use a primary amine or ammonia. I want to put that in there too. And we produce the amine. And the last step involves the proton transfer, where we remove a proton from the nitrogen. Whereas when we form an enamine, okay, we use a secondary amine. And the last step involves a proton transfer on a carbon that is next to the carbon of the double bond. So again, here we have primary or ammonia. Here we have a secondary, and tertiary is not going to do anything. Okay, so we don't have to worry about that. Before we move on, I just noticed something funny in my slides here. You know, my students tell me all kinds of things that they come up with to remember stuff. It's a little harder over Microsoft Teams. It's easier when I'm just walking around the classroom and talking to my students. But here's what I have written, and you can either laugh at this or you can maybe try and use this. But for imine, they have imine is the way a student wrote it, like that. So the number 1, so it means it's a primary amine. And then for the enamine, what they did was this. There's not a lot of room down here, but they took the number 2 and they were enamine. Okay, and then they went like this. They turned it into the number 2. So again, you can see the number 2 is here, you know, the number 1. So imine and enamine, I don't know if it helps you. Hey, that's great. And if you're just like, you know what, but at this point, Mr. Dion, my photographic memory is on point, so I don't really need that. But whatever. Anyhow, it was taught to me by my students. All right. I want to show you a new way to convert a ketone rather, into an alkane. We learned the Clementine reduction. If you remember, it was the zinc mercury amalgam with HCl, the Clementine reduction. Well, there's another type of reduction that we can use to reduce a carbonyl all the way to an alkane, and it's called the Wolff-Kishner reduction. It's a really old reaction, but you can imagine that if it's in a first-year textbook, you know, a first-year organic chemistry textbook, it's a really important reaction in organic chemistry. So the way that we do this, the reason that it shows up here, if you're like, what's this got to do with the imine and the enamine? Well, you're actually forming an imine. Okay, so what you're doing is you take a catalytic amount of acid, but instead of a primary amine, you take this compound here. When you have this compound, so if you have NH2, NH2, this is called hydrazine. Hydrazine. Okay, and then you make a new functional group. This functional group, maybe I'll write it down here, when we have a nitrogen like this, okay, and like that. We call this a hydrazone. So you go from a ketone to a hydrazone. So this is a hydrazone on that cyclohexane ring. Then the next step, you simply, and this is proof that it's old-fashioned, right? All they had was potassium hydroxide, right? They probably even isolated it from ashes. I'm kidding. But anyhow, it's a really old reaction. What did they do? They just took it and heated it up with sodium hydroxide and checked what happened. Well, notice that you end up losing nitrogen, right? You lose N2. Well, nitrogen is a gas, so you know the reaction is irreversible. So that's kind of cool. It's probably really high yielding. Well, look, 80% yield. That's very, very good. But again, the first step is the imine formation. And I guess that our book is actually calling this an imine. Again, it's called a hydrazone, but it's like an imine, right? If you consider that in our group, it is like an imine. Now, if you're wondering what the mechanism here, it's the exact same as imine formation. So what have we got? We took the ketone, we used a catalytic amount of acid, hydrazine, we lose water, we form this imine, which is also called a hydrazone. Then we treat it with potassium hydroxide and heat. So potassium hydroxide is going to be dissolved in water. And we end up just removing, I'm having a problem with my Teams on my MacBook. So it's telling me I have to quit it. So just bear with me if I conk out or something. Yeah, it might kick me out. But either way, I'm still on my iPad. So no worries there. Anyhow, so we end up losing nitrogen and we just reduce this to the alkane. Now, if you're wondering, you know, what kind of mechanism is this? You know, actually the mechanism, and I don't like to use the word simple with next to the word mechanism, because I don't think any mechanism is super simple, but it's actually just a bunch of proton transfers, really, with the loss of nitrogen. So you see how you start out with the hydrazone or the imine, whatever you want to call it, and it's got 2 hydrogens. What's going to happen is the base is going to rip both of those off. So you rip off the first one, okay, you take the first one off. Where's my highlighter? Okay. You make a negative charge on the nitrogen, you make a double bond. Then you take a pair of electrons, you put them down on the carbon. So that's going to rip off a proton. You do it again. You rip off the second proton, makes a negative charge in the nitrogen, make the triple bond. Then you end up losing nitrogen. So right here, they could have put minus N2. I know it says nitrogen is expelled here, but anyhow. Then you make another carbanion and it rips off another proton. I know that when you're just learning the subject of organic chemistry, like we're doing, it might not seem like the most simple mechanism, but if you really break it down, I mean, it's 4 proton transfers and loss of nitrogen. And I always felt like as a student, it was pretty easy to remember that you were going to lose nitrogen because you're starting it with something that has 2 nitrogen atoms attached, and then you end up with no nitrogen at all in the end. So I always found like the Wolff-Kishner was a memorable mechanism is maybe the way I could put it. All right, let's go back here. You check out the similarities between these different acid catalyzed mechanisms that we have discussed. Now, whenever you're practicing your mechanisms, you want to make sure that if you're in acidic conditions, okay, when you're using an acid as a catalyst, every reaction species should either be neutral, have no charge, or have a +1 formal charge. Okay, if you end up with something that overall is negative, you have gone down the wrong path. You remember those book Choose Your Own Adventure? Well, you've chosen the wrong path. Okay, you're in the wrong spot. You always want to have something that's neutral or positively charged. With all that in mind, I think the best thing you can do with nitrogen nucleophiles would be to train your eye to recognize, what's going to happen. And it says here in question 19.15, predict the major product for each of the following reactions. So here we have a ketone. The second one we have a ketone. So we got ketones in both of them. The first one we have ammonia. The second one we have a primary amine. So what are we going to form here? If we're using a ketone in both questions and ammonia or a primary amine, we're going to be forming an imine. So this involves imine formation. Okay, I could even move this down here maybe. So imine formation. And what's the functional group? What does an imine look like? An imine looks like this. You've got a carbon with a double bond to nitrogen. So I'll use a bond line structure. So we have a carbon with a double bond to nitrogen. We've got R groups. They might be the same. They might be different. And then here we've got another R group or hydrogen if we're using ammonia. So with that in mind, if we take a look at the first one, we're starting with this molecule, which is cycloheptanone. What are we going to end up with? Well, our 7-membered ring is going to stay intact, our cycloheptane ring, like that. But now instead of a double bond to oxygen, we're going to have a double bond to nitrogen, like this. And our R group, since we're using ammonia, is going to be a hydrogen. And that is the compound that we're going to form. All right, so that's a ketone plus ammonia. Now, if we take this molecule, this is cyclopentanone. This is cyclopentyl amine. We'll talk about amine nomenclature later on in the class. But look, all you have to do is kind of connect the dots. Look, first we're going to start by drawing out the ketone. So let's draw the ketone skeleton is what I should have said. Now, instead of a double bond to an oxygen, it's not an oxygen. We're going to have a double bond to what? A nitrogen. And what's the R group going to be on the nitrogen? It's going to be all of this, right? Because you have to lose these 2 protons to make water. So let's draw our R group, and our R group is a cyclopentyl, like that. Give me a thumbs up if you follow me on those 2. Forming an imine using a catalytic amount of acid, ketone or aldehyde, ammonia, or a primary amine. All right, it's kind of like, kind of connecting the dots here a little bit. The reason why I encourage you to do it this way is because to draw the mechanism every time to try to figure out what's going on would be a little painful, I think. That would be a little bit time consuming. I don't think there's any need of doing that with, in fact, most of the reactions that we look at in this class. All right, well, let's move on from there. Let's try question 19.17. Look, again, we have 2 ketones, right? We have a ketone here and a ketone here. We're using a catalytic amount of acid. And instead of a primary amine, you see in the second one, we're using hydrazine. And here we're using NH2OH. That's called hydroxylamine. I'll write it down up here. But it's going to behave the same way a primary amine would, right? Hydroxylamine. Right? It's as if you had NH2 and then R, but your R is an OH. That's all it is, okay? So again, we're going to form imines, right? So let's write down the structure of an imine. So this, again, is imine formation, like that. So what does an imine look like? We've got a double bond to a nitrogen. We've got a couple of R groups, like this. And then we've got another R group here and a lone pair. And the R group could be, it could be a carbon-based group. It could be a hydrogen. It could be a hydroxyl. It could be and NH2 depending on the situation. So for the first one, let's start by drawing the carbon skeleton. I've got the 5 carbons like this. Instead of a double bond to oxygen, I've got a double bond to my nitrogen. And what's attached to my nitrogen? A hydroxyl. So there you go, like this. And the reason why I put this question in here is because this introduces you to yet another functional group. This is called an oxime or an oxime, depending on who you ask. But this is called an oxime, okay? We have this kind of arrangement right here. Anyhow, and if you're wondering, like, what the heck do you use these kinds of things for? You can use them to make a heterocycle like this. This is called isoxazole. So isoxazole, which is a ring it's an aromatic ring that's not uncommon in some drugs. Anyhow, let's see, what are we doing in the next one? We're taking our ketone, we're treating it with hydrazine. We've seen this already today, so there's nothing new under the sun, right? We're going to start with our carbon skeleton. We've got our double bond. It's to a nitrogen. And what's our R group? Well, it's going to be NH2. So let's write that in here like that. And that's our hydrazone. And that can be used to make, so this is our, again, this is our hydrazone. I'll leave it out because the book calls it an amine. But either way, that can be used to make compounds like this. So this is called oxodiazole. And again, this isn't covered in the textbook. It's just for fun. So oxodiazole. Anyhow, in case anybody here is interested in heterocycles, kind of fun stuff there. All right, we're still moving on here with the questions. And the reason why we have to keep going is because we haven't talked about enamine formation yet, right? So this is enamine formation. All right, we're starting with a ketone in each case. We have a secondary amine here. We have a secondary amine here, even though it's in the same molecule. And we're going to make an enamine. So what does an enamine look like? It looks like we've got our carbon with a single bond to nitrogen, but we've got a double bond over here, a single bond over here, and then we've got our R group and another R group like that. I'll just break those bonds like that. And where the double bond is, okay, that's attached to the carbon that was originally attached to the oxygen. Okay, so that's an enamine. So if we're taking a secondary amine, this is dicyclohexylamine, but this is a secondary amine, and we have a ketone. Let's start by drawing the skeleton of our ketone, which has 5 carbons in a ring. Now, instead of a double bond to oxygen, we've got a single bond to nitrogen. We've lost water, so we've got our 2 R groups that are attached to our nitrogen. So we've got our 2 cyclohexyl rings. So we'll put those out here like that. Now, where's the double bond going to be? The double bond is going to be attached to the carbon that had the oxygen originally. It's going to be down here. Okay, so I'll put it like this. And that is our enamine. Enamine. All right, now the next one is a little trickier because you have to make a ring, right? You see that the ketone and the amine are in the same, they're in the same place, right? Well, we need to have a nucleophilic attack as our first step. And the nucleophile is the nitrogen, and it's going to attack the carbonyl like this. Okay, we're going to attack that carbonyl, then eventually we're going to make a carbonyl amine. So how many carbons are, or how many atoms, I should say, are going to be in our ring? Look, let's count. We've got 1, 2, 3, 4, 5. So here's how I would solve it. I would write out the phenyl aromatic ring because it hasn't changed at all. And then I would put a 5-membered ring. So 1, 2, 3, 4, 5, like that. Okay, now let's see here. If I count these out, 1, 2, 3, 4, 5, my 5th atom has to be a nitrogen, or where position 5 is. So I'll put my nitrogen in here. On carbon number 3, I've got the 2 methyl groups. So I'll put those over here. And on my nitrogen, I'm going to have an ethyl group too, like that. Well, where is the double bond going to be? The double bond, remember, is going to be attached to the carbon of the carbonyl. it can't be on this side because then you'd have a carbon with 5 bonds. That's impossible. So it must be between carbons 1 and 2. And that is correct. That's where it is. So let's pencil it in here between carbon 1 and 2 like that. And that is our enamine. Don't believe me? Look, you've got the carbon nitrogen bond. You've got a double bond here, single bond here, and here's one R group. And this is your second R group. It just happens to be tied into the enamine like that. All right. Give me a thumbs up if you follow me on those two. If you have a question, of course, don't be shy to stop me and say I'm not quite sure how you connected that together. When you're making rings, you know, you really got to count kind of carefully and be meticulous, which makes me wonder how I became an organic chemist, because I'm not the most meticulous guy. But I remember one of my professors telling me, he said, if you want to survive in organic chemistry, which I think you do, you know, and you want to work in a lab, you've got to develop a little bit of an eagle eye. You know, you kind of always got to be on the lookout and be an astute counter of atoms, I guess. All right. Well, that covers the section on nitrogen nucleophiles. So what did we learn? We learned imine formation. We learned enamine formation. We talked about how an imine is called a shift base. We talked about, what else? We talked about hydroxylamine and hydrazine, these two new molecules. We talked about what an oxime is, or an oxime. I always call it an oxime. And we talked about a hydrazone, which again is a type of amine. So that's what we learned here. And we looked at the mechanism for the formation of an enamine and an imine. And we saw how they really were identical, except for the last step, where there was a slight difference in the last proton transfer of the mechanism. Well, I want to go all the way back to the whole section on oxygen nucleophiles. Remember what we did in that section, section 19.5? What did we make? We ended off looking at how to make acetals, right? We spent quite a bit of time talking about an acetal. Now, if you forget what an acetal is, here's one right here. Here's another one down here. It's like you've got a carbon. Okay, I'll go with this one down here. It's like you've got a carbon that's got two ethers attached to it. Right? It's like you've got an ether here and then another ether here. Anyhow, that's one way of viewing it, if you will. But you remember that we talked about how to form an acetal. You take, you know, your diol, like ethylene glycol. We looked at that. Or you can use an alcohol and just two equivalents. You treat it with a strong acid. You heat it up and you remove water. Right? That was how we made an acetal. Well, we can also hydrolyze an acetal. And we actually talked about that a little bit. We said, okay, well, you can take an acetal and you can treat it with dilute aqueous acid. Here they have H2O and then they have H plus in brackets. If you were to just write H3O plus, if you just wrote H3O plus, I would give that 100%. There's nothing wrong with that. But either way, the acetal gets hydrolyzed back to the ketone and we end up releasing the two alcohols. So this is the reverse of what we looked at in section 19.5 when we talked about acetal formation. Another cool thing about acetals, and I've made plenty of acetals in my life, is that you don't have to be very careful around them when you're using a strong base. They're very resistant to strong base. They're very labile in acid. You got to be careful with acid, but in strong base, you don't have to fret. They're going to resist that. Well, if you've wondered what the mechanism would be for this reaction here, how would I blow that acetal apart? Let's take a look. If you take a look, the first step is a proton transfer to convert one of the alkoxy groups into a good leaving group, right? An alcohol is the conjugate base of a strong acid, right? If you have a protonated alcohol, it's going to have a pKa of around -2 or around that region. Then we have water coming in and acting as a nucleophile. And you can see how we're blowing the whole thing apart, right? We get a couple of proton transfers. We lose the second molecule of alcohol. Then we end up with a protonated carbonyl. We do a proton transfer, and we're back to our ketone. Now, if you've been studying over the past few days, you've probably noticed something about this immediately. You probably noticed that this mechanism is the reverse of acetal formation, right? If you spend some time practicing the mechanism of acetal formation, you probably noticed that this is the exact reverse of it, right? What's the first step of forming an acetal from a ketone? The proton transfer, right? To make the protonated carbonyl and render it highly reactive or highly electrophilic. So we can also do the same thing with an imine and an enamine. So whether you are dealing with an acetal or an imine or an enamine, you can go right back to the starting carbonyl, whether it's a ketone or an aldehyde, just by treating the compound with dilute acid. So again, you see here they have, H plus and H2O. The same thing here. You could just write, H3O plus. That counts. But you can see how you've got to be, again, kind of astute, especially when we look at enamines in terms of drawing the product of the hydrolysis of the enamine, right? Again, this is an imine, and this is an enamine, okay? So when you hydrolyze, it's easy to draw the squiggle line between the double bond and then say, okay, well, I've got an oxygen up here, but it's a little trickier here, right? You draw the squiggle line. This is the bond that's breaking between the carbon and nitrogen, but the double bond goes back there, okay? And you lose this double bond. All right. So if you're wondering about the hydrolysis of an imine and an enamine, this is all based off of something called the principle of microscopic reversibility, which is that the mechanism in one direction is going to be the exact same mechanism in the opposite direction. Okay. So if you look at the formation of the imine and the enamine, their hydrolysis is just going to be the reverse. So with all that in mind, I want to take a look at a problem that involves some acetals, involves an imine and an enamine. So what we're doing in all of these is just the hydrolysis, okay? So you see how every single one of these has the same reaction conditions, just dilute acid. The first one, we have an acetal. The second one, we have an imine. In this one, we have another acetal. Okay, and in this one, we have an enamine. So what did we do when we have an acetal? So this seems to be tricky for students sometimes. Remember what an acetal is, right? An acetal is when you have a carbon that's got it's got two ethers attached to it, okay? This is the carbon in question, and when you hydrolyze that acetal, with H3O plus, you end up with this where you have the carbonyl reinstated, okay, if you will. So if you look at the carbon, hopefully you can tell that this is the carbon. That's the magic carbon right there. It's the one that has an ether here, a bond to, right? You can see this is like an ether here, and then this is like an ether here. So it's like we got two ethers. So that carbon is going to go back to being a carbonyl. So that means that one of the products here, because it's telling us to draw both products, one of the products is going to be the 5-membered ring. And now we've got our double bond to our oxygen. Now, what else do we get besides this? We also get two equivalents of these as alcohols. So two equivalents of ROH. So what's our R group here? We have the oxygen with one R group, and you can see the other oxygen is attached to the same R group. So the two alcohols you're going to get are both going to be in the same molecule. You're going to get a hydroxyl, then you've got 1, 2, 3 carbons. If you want to draw it like this, if it helps you to go like this, there you go. Come on. There's the diol that you get back. So those are the two products of this first reaction. All right. And these are tough questions for me to ask you, over Microsoft Teams. With the imine, what do? We break the bond between the carbon and the nitrogen, and we put an oxygen there on the side that has the two R groups. So let's draw that R group. So it's going to look like this, that, and now we've got a double bond to oxygen like this. What else do we have? We're going to produce our amine. Since it's an imine and we have an R group on here, we're going to have a primary amine, which is going to be methylamine. So CH3NH2. The next one, where's our acetal? The magic carbon, the one that has the two ethers, is this one here that I have highlighted in red. The R groups this time are just two little measly hydrogens, but that's what it is, okay? So you're going to end up putting a carbonyl on here and breaking that bond. So that means that one of the products from this is simply going to be a carbon with a double bond and two hydrogens. That's formaldehyde, right? That's the simplest possible aldehyde you can have. And then the diol that you're going to get, again, you can see that the alcohols are both tied in. They're tied together, right? So you're also going to end up with this, where you've got, try to draw it properly here, like this. And you've got these CHEM dimethyls, like that. And then for the last one, we have an enamine. Remember, when you have an enamine, what's the bond you break? The bond between the carbon and the nitrogen. It's a single bond. This double bond is going to disappear. So let's take a look. We're going to break this bond right here. This bond's going to disappear, and we're going to have a double bond to oxygen here. So let's do that. I'll try to draw the bicyclic species the best I can. There we go. So now we have the double bond to oxygen. And our secondary amine is going to be nitrogen with 2 methyl groups. And so it's got to have a nitrogen on it like that. All right. Are there any questions about the hydrolysis of imines, enamines, and acetals that we're looking at here? Section 19.7 only deals with hydrolysis. Right? We spend section 19.5 learning about how to make an acetal. We spend section 19.6 learning how to make an imine and an enamine, also an oxime or an oxime, and a hydrazone, whatever. And then section 19.7 is all about hydrolysis. Okay, it's got nothing to do with anything else but hydrolysis, just blowing all these things apart, which always uses the same conditions. You just treat it with dilute acid. But if you go back to sections 19.5 and 19.6, when we formed all these imines and enamines, we end up, well, that's not formation. Where are they? Anyhow, we always end up doing what? We lose water, whether we're forming an enamine or an imine or an acetal. So that stands to reason that based off of Le Chatelier's principle, if we want to hydrolyze these, we have to add water. So we're adding water and acid, right? It's basically just an equilibrium. If you want to make an acetal or an imine or an enamine, you have to remove water from the reaction mixture. If you want to hydrolyze it, you're going to add water to the reaction mixture. All right. Does everybody follow me on that? Because I want to move on to section 19.8, which doesn't have any mechanisms in it at all. And it deals with sulfur chemistry.